Hello there, and welcome. Perhaps you've had a long day, or maybe you simply find comfort in the gentle rhythm of ocean stories. Either way, tonight's journey is for you. There's nothing you need to do but rest. Let your shoulders soften, your breathing slow, and your thoughts drift like currents in warm water. Tonight we're gliding through the peaceful world of rays and manta rays, creatures whose grace has captivated ocean lovers for generations. These gentle beings move through the water with such elegance that watching them feels almost meditative. From the enormous manta rays that seem to fly through open water, to the quiet stingrays resting beneath the sand, to the spotted eagles that leap from the surface in displays of unexpected beauty, each has adapted to life in the ocean in its own remarkable way. But before we jump in, if you enjoy learning about our oceans, you're welcome to let us know where you're tuning in from and what time is it for you. It's always fascinating to see how far our stories reach. And if these quiet ocean journeys help you unwind, you're always welcome to subscribe so you can drift off with us whenever you need. Now, let your body grow a little heavier as we begin. In the vast timeline of ocean life, few creatures have endured as long as the rays. These animals belong to an ancient group called cartilaginous fish, a lineage that stretches back more than 395 million years, deep into a geological period known as the Devonian. During this distant age, the world's oceans were warm and shallow, covering vast portions of what would one day become dry land. In these primordial seas, the first cartilaginous fish began to appear, ancestors to both modern sharks and rays. Unlike most fish that would come after them, these early creatures did not develop bones. Instead, their skeletons were composed entirely of cartilage, the same flexible material that forms the tip of your nose or the structure of your ears. This might seem like a primitive trait, something left over from an earlier, less evolved time, but cartilage is actually an elegant solution to the challenges of ocean life. It's lighter than bone, which helps with buoyancy and makes movement through water more efficient. It's flexible, allowing for greater range of motion, and perhaps most importantly, it's strong enough to support even very large bodies while remaining energy efficient to produce and maintain. The rays we see today represent one of the most successful branches of this ancient family tree. They are part of a group called batoids, and they number more than 600 species spread across 26 families. This makes them the largest group of cartilaginous fish in the world, even outnumbering their close relatives, the sharks. While sharks retained a more cylindrical torpedo-like body shape optimized for speed and predation in open water, rays took a different evolutionary path. They became flattened, with bodies that spread wide rather than stretching long. Their pectoral fins, which in most fish are relatively small appendages used for steering and balance, grew enormous in rays, extending outward and fusing with the sides of the head to create wing-like structures. This transformation from the ancestral shark-like form into the distinctive ray shape happened gradually over millions of years. Fossil evidence suggests that the earliest recognizable rays appeared during the Jurassic period, roughly 150 to 200 million years ago. At this time, much of what is now Europe was submerged beneath warm, shallow seas, creating an environment that resembled today's Caribbean or South Pacific island chains. These ancient seas were rich with life, teeming with invertebrates that lived on or just beneath the seafloor. For a fish that could flatten itself, hide in the sand, and ambush prey from below, this was an ideal habitat. The oldest confirmed ray fossil is a creature called Antiquobatis, discovered in sediments from Germany that date to the Jurassic. This fossil shows the characteristic flattened body and enlarged pectoral fins that define modern rays, though it also retains some features that would be lost in later species. Over time, rays diversified into many different forms, each adapting to specific ecological niches. Some became specialists at crushing hard-shelled prey like mollusks and crustaceans. Others evolved to filter tiny organisms from the water. Still others developed electric organs capable of stunning prey or defending against predators. The diversity of rays today is a testament to the success of their basic body plan. There are stingrays, which bury themselves in sand and possess venomous barbs for defense. There are electric rays which can generate powerful shocks. There are sawfish, with long, tooth-studded rostrums that they swing through schools of fish. There are guitarfish, which retain a somewhat shark-like appearance. And then there are the eagle rays and manta rays, which abandoned the bottom-dwelling lifestyle entirely and took to the open water, where they swim with powerful bird-like wing beats. What unites all these different rays is their fundamental anatomy. Every ray has a flattened body, though the degree of flattening varies. Every ray has pectoral fins that extend along most of the body length and merge with the head. Every ray has gill slits located on the underside of the body, rather than on the sides as in sharks. And every ray has eyes and spiracles, small openings used for breathing, located on the top of the head. This arrangement makes perfect sense for a bottom-dwelling animal. With eyes on top, a ray can watch for predators from above even while buried in sand. With gill slits below, it can draw in clean water through the spiracles on top and expel it through the gills below, avoiding the risk of clogging its respiratory system with sediment. The skeleton of a ray, like that of all cartilaginous fish, contains no true bone. Instead, it's composed of cartilage that is often strengthened and hardened by deposits of calcium. This calcified cartilage is rigid enough to support the body and provide attachment points for muscles, but it remains lighter and more flexible than true bone. The lack of heavy bones contributes to a ray's buoyancy, but unlike bony fish, rays don't have swim bladders, the gas-filled organs that allow most fish to hover effortlessly in the water column. Instead, rays must either keep moving or rest on the bottom. Many rays have evolved large, oily livers that help with buoyancy. The liver of a manta ray, for example, can account for a significant portion of its body weight, filled with lipids that are less dense than water. The skin of a ray is covered with tiny tooth-like scales called dermal denticles or placoid scales. These are similar to the scales found on sharks and are structurally more like teeth than the scales of bony fish. Each denticle has a base embedded in the skin and a pointed tip that projects outward. In most rays, these denticles are quite small and create a sandpaper-like texture. In some species, certain denticles have become enlarged into tubercles or spines that run along the back or tail. The infamous barb of a stingray is actually a highly modified, enlarged dermal denticle that has become serrated and associated with venom-producing tissue. Rays reproduce in ways that are unusual among fish. All rays practice internal fertilization, meaning that males transfer sperm directly into females rather than simply releasing it into the water, as most bony fish do. Male rays possess a pair of claspers, modified portions of the pelvic fins that are inserted into the female's reproductive opening during mating. This internal fertilization allows rays to produce fewer, larger, more developed young that have a better chance of survival. Some rays lay eggs enclosed in tough, leathery cases that are sometimes called mermaid's purses. These egg cases are deposited on the seafloor, where the embryos develop over a period of weeks or months before hatching as miniature versions of adults. Other rays retain the eggs inside their bodies and give birth to live young. In these species, the embryos may be nourished by a yolk sac, by uterine secretions, sometimes called uterine milk, or in a few cases by a placenta-like structure. The evolution of rays has been shaped by the environments they inhabit. Most rays are marine, living in salt water from the shallows to great depths, but some species have adapted to freshwater. The river stingrays of South America, for instance, live exclusively in rivers and have never been found in the ocean. These freshwater rays likely evolved from marine ancestors that gradually adapted to lower salinity levels, eventually becoming trapped in river systems as sea levels changed or land connections formed. Today, freshwater stingrays can be found in parts of South America, Africa, and Southeast Asia, each population representing an independent evolutionary transition from sea to river. Throughout their long history, rays have remained remarkably successful. They have survived multiple mass extinction events that wiped out many other groups of animals. They have adapted to nearly every marine habitat, from tropical coral reefs to cold polar seas, from shallow tide pools to the abyssal depths. Their flattened bodies, efficient swimming, and diverse feeding strategies have allowed them to thrive in a changing world for hundreds of millions of years. And today, despite facing new challenges from human activity, rays continue to glide through the world's oceans, living testaments to the enduring power of their ancient design. To understand how a ray moves through water with such effortless grace, we must first understand the architecture of its body. A ray is essentially a living wing, its entire form optimized for a swimming style that resembles flight more than the tail-propelled motion of most fish. The pectoral fins, which in a typical fish are small appendages near the front of the body, have in rays expanded dramatically. They stretch from the head all the way to the tail, creating a broad, flat disc that can measure anywhere from a few inches across in small species to more than 20 feet in the largest manta rays. These enormous pectoral fins are not simple flaps of skin. They contain an internal skeleton of cartilaginous rods called radials, which extend outward from the body like the spokes of a fan. These radials provide support and allow the fin to maintain its shape even under the stresses of swimming. Between and attached to these radials are thin, flexible cartilaginous rods called ceratotrachea, which extend all the way to the edge of the fin and give it flexibility. Muscles attached to the radials allow a ray to control the shape and movement of its pectoral fins with great precision, creating the undulating waves that propel it through the water. The way a ray swims depends on its size and lifestyle. Smaller rays that live on the bottom often use a motion called undulation, in which waves pass along the pectoral fins from front to back or from side to side. This creates a gentle rippling motion that can be quite slow and controlled, allowing the ray to maneuver in tight spaces or hover just above the seafloor. Larger rays, especially those that have taken to open water like eagle rays and manta rays, use a different technique called oscillation. Instead of creating waves along the fin surface, they flap their pectoral fins up and down in powerful strokes that resemble the wing beats of a bird. This allows them to generate much more thrust and reach higher speeds. A manta ray in full flight through the open ocean is a magnificent sight, its enormous wings beating with surprising power, creating a smooth, gliding motion that can carry it long distances with apparent ease. The head of a ray is fused with its pectoral fins, creating a continuous disc without a clear boundary where the head ends and the body begins. The mouth is located on the underside of the disc in most species, positioned perfectly for feeding on bottom-dwelling prey. In manta rays and their close relatives, however, the mouth has migrated to the front of the head, where it can more easily filter plankton from the water. The jaws of a ray vary depending on diet. Species that feed on hard-shelled prey like mollusks and crustaceans have powerful jaws equipped with flat, plate-like teeth designed for crushing. Some species have teeth arranged in pavement-like patterns, with each tooth fitting snugly against its neighbors to create a solid crushing surface. Other rays that feed on softer prey have smaller, more pointed teeth, or in the case of manta rays, tiny vestigial teeth that play no role in feeding. The eyes of a ray are positioned on top of the head, giving the animal a wide field of vision above while it rests on or swims near the bottom. This placement is ideal for watching for predators like sharks that might attack from above. However, it also means that a ray cannot see what's directly in front of its mouth. To compensate, rays have evolved an array of sensory systems that allow them to detect prey without seeing it. The most important of these is electroception, the ability to sense the weak electric fields generated by living organisms. All rays possess specialized sensory organs called ampullae of Lorenzini, which are located in pores on the underside of the disc, particularly around the head and mouth. These ampullae are incredibly sensitive. They can detect electric fields as weak as a few billionths of a volt per centimeter, allowing a ray to sense the muscle contractions and nerve impulses of prey buried beneath the sand. When a ray glides slowly over the seafloor, it is essentially scanning the ground below with an electric sense, searching for the telltale signals of hidden clams, crabs, or worms. Once prey is detected, the ray positions itself above the spot and uses its pectoral fins to create a suction force that pulls the prey out of the sediment and into its mouth. This feeding technique, sometimes called tenting, involves the ray lifting its head while pressing the edges of its pectoral fins against the bottom, creating a sealed chamber into which sand and prey are pulled. Just behind each eye is a spiracle, a small opening that leads directly to the gills. For a bottom-dwelling ray, the spiracles are essential. If the ray breathed through its mouth like most fish, it would risk inhaling sediment every time it took a breath. Instead, water is drawn in through the spiracles on top of the head, passed over the gills where oxygen is extracted, and expelled through the gill slits on the underside. This allows a ray to breathe even when its mouth is pressed against the seafloor or filled with food. In rays that have abandoned bottom dwelling and swim constantly in open water, the spiracles are smaller and less important, as these rays can breathe through their mouths without risk of sediment intake. The tail of a ray varies greatly depending on the species. In stingrays, the tail is typically long, thin, and whip-like, equipped with one or more venomous barbs near the base. This tail is primarily a defensive weapon. When threatened, a stingray can whip its tail upward and forward with surprising speed and force, driving the barb into whatever is threatening it. The barb itself is a modified scale, covered in a thin sheath of skin that contains venom-producing tissue. When the barb penetrates flesh, this sheath ruptures, allowing venom to flow into the wound. The venom contains a mixture of proteins and enzymes that cause intense pain, tissue damage, and in severe cases, dangerous effects on the heart and nervous system. However, it's important to note that stingrays are not aggressive animals. They use their barbs purely in self-defense, and most stingings occur when a person accidentally steps on a buried ray. In manta rays and some other species, the tail is much less formidable. Manta rays have no barb at all, just a long, thin, whip-like tail that trails behind them as they swim. This tail serves no defensive or propulsive function and is essentially a vestigial structure, a remnant of their evolutionary past. In eagle rays and cownose rays, the tail typically has one or more barbs, though these species spend most of their time swimming rather than lying on the bottom, so the defensive barb is less commonly used than in true stingrays. The coloration of rays shows interesting patterns related to their lifestyle. Most bottom-dwelling rays are dark on top and pale on the underside, a color scheme called countershading. When viewed from above, the dark dorsal surface blends with the dark seafloor or the darkness of deep water. When viewed from below, the pale ventral surface blends with the bright surface waters. This camouflage helps rays avoid predators and also helps them approach prey undetected. Some rays have elaborate patterns of spots, rings, or lines on their dorsal surface, which may serve to break up their outline and make them harder to see against a complex background of rocks, sand, and vegetation. Manta rays, which spend most of their time in open water, tend to be darker on top and lighter below, but many also have distinctive markings on their ventral surface. These markings are unique to each individual, rather like fingerprints, and researchers use them to identify and track individual mantas over time. The size range among rays is remarkable. The smallest species are tiny skates and stingrays that might span only 6 or 8 inches across, small enough to fit in the palm of a human hand. At the other extreme are the giant manta rays, which can reach wingspans of more than 20 feet and weigh well over a ton. Despite this huge variation in size, all rays share the same basic body plan, the same flattened disc, the same enlarged pectoral fins, the same ventral gill slits and dorsal eyes. It is a design that has proven adaptable to an enormous range of sizes and lifestyles, from the smallest bottom dweller to the largest filter feeder. One of the most fascinating aspects of ray anatomy is the brain. Rays have relatively large brains compared to their body size, larger than most other fish. Within the ray brain is a region associated with learning, memory, and sensory processing that is more developed than in many other fish groups. This suggests that rays are capable of complex behaviors, and indeed, observations support this. Rays have been seen using tools, a behavior once thought to be restricted to mammals and birds. They appear to recognize individual humans and can be trained to respond to visual cues. Manta rays have even demonstrated self-awareness in mirror tests, a cognitive milestone that very few animals achieve. The combination of large brains, complex sensory systems, and adaptable behavior makes rays far more than simple, instinct-driven animals. They are intelligent, aware, and capable of learning from experience. Among all the rays, few inspire as much wonder as the mantas. These are the giants of the ray world, creatures of such size and grace that encountering one underwater feels almost otherworldly. There are currently 3 recognized species of manta ray, all belonging to the genus Mobula, though for many years they were classified in their own genus called Manta. The giant oceanic manta ray, Mobula birostris, is the largest, with a wingspan that can reach 26 feet and a weight that can exceed 2 tons. The reef manta ray, Mobula alfredi, is somewhat smaller but still impressive, typically reaching wingspans of 11 to 15 feet. And the newest recognized species, Mobula yare, has a size intermediate between the other two. What sets manta rays apart from their relatives is not just their size but their lifestyle. While most rays are bottom dwellers that spend their time resting on or swimming just above the seafloor, manta rays have abandoned the bottom entirely. They are pelagic, meaning they live in the open water column, and they swim constantly. A manta ray cannot rest on the seafloor like a stingray can. It must keep moving, keep its enormous pectoral fins beating, in order to push oxygenated water over its gills. This is because manta rays, like some sharks, are ram ventilators. They lack the muscular pump that most fish use to actively draw water over their gills. Instead, they rely on forward motion to force water into their mouths and out through their gill slits. This need for constant motion shapes every aspect of a manta's life. They are tireless swimmers, crossing vast expanses of open ocean with a steady, powerful wing beat that can carry them hundreds or even thousands of miles. Tagged manta rays have been tracked making long-distance migrations, though the reasons for these journeys are not fully understood. It's likely that mantas follow concentrations of plankton, their primary food source, which shifts with currents, seasons, and oceanic conditions. Some populations appear to be resident, remaining in the same general area year-round, while others are highly migratory, appearing in certain locations only at specific times of year. The body of a manta ray is perfectly designed for its lifestyle. The pectoral fins are enormous, triangular, and slightly curved with pointed tips that trail behind the body. Unlike the rounded, disc-like pectoral fins of bottom-dwelling rays, a manta's fins are more like the wings of a bird or airplane, with an airfoil shape that generates lift. As the manta flaps these wings downward, it pushes water backward and downward, creating thrust that propels the animal forward and upward. The recovery stroke when the wings sweep upward is less powerful but still contributes to forward motion. The overall effect is a smooth, efficient swimming style that can be maintained for hours without rest. At the front of the manta's head are two distinctive structures called cephalic fins or cephalic lobes. These look like horns or antennae, extending forward from either side of the mouth, and they give manta rays one of their common names, devil rays. In reality, these cephalic fins are highly modified portions of the pectoral fins that have specialized for feeding. When a manta swims normally, the cephalic fins are curled into tight spirals that point forward and slightly downward. But when the manta begins to feed, these fins unfurl and extend outward, forming a wide funnel that channels plankton-rich water directly into the mouth. Manta rays are filter feeders, meaning they strain tiny organisms from huge volumes of water. Their diet consists primarily of zooplankton, the drifting masses of small animals that include krill, copepods, mysid shrimp, and the larval forms of crabs, fish, and other creatures. To capture these tiny prey items, a manta must process enormous quantities of water. As water flows into the mouth and over the gills, it passes through specialized filtering structures called gill rakers. These are rows of thin, fleshy plates covered with a spongy tissue that traps plankton while allowing water to pass through. Once trapped, the plankton is directed toward the throat and swallowed. The feeding behavior of manta rays is wonderfully varied. Sometimes a lone manta will swim in a straight line just beneath the surface, mouth agape, cruising through a cloud of plankton. Other times, mantas will perform barrel rolls, somersaulting through the water again and again to stay within a concentrated patch of food. This rolling motion creates a current that helps concentrate the plankton, making each pass more productive. When plankton is especially abundant, mantas will sometimes engage in chain feeding, a spectacular behavior in which multiple individuals swim in a circle or spiral, each following the one ahead, mouths open. This creates a cyclone effect that traps plankton in the center of the formation, allowing each manta to swim through the same concentrated food repeatedly. Another remarkable feeding strategy involves feeding at depth. While manta rays are often seen near the surface, they are also capable of diving to considerable depths. Reef manta rays have been recorded diving to depths of over 400 meters, while oceanic mantas likely go even deeper. At depth, they encounter different assemblages of zooplankton, including animals that migrate vertically through the water column each day, rising toward the surface at night and descending during the day. By diving, mantas can access food sources unavailable to surface feeders. Manta rays are highly social animals. Often seen in groups, these aggregations can be small, just 2 or 3 individuals swimming together, or they can be large, with dozens of mantas gathered at a particularly rich feeding site or cleaning station. Cleaning stations are specific locations, usually near coral reefs or rocky outcrops, where mantas go to have parasites and dead skin removed by small, cleaner fish. A manta will approach a cleaning station and hover in the water, sometimes using its pectoral fins to hold itself in place against a gentle current. small fish, typically wrasses, then swim over the manta's body, picking off parasites and taking bites of dead or damaged skin. A manta may remain at a cleaning station for an hour or more, patiently allowing dozens of cleaner fish to work over its body. Many individual mantas return to the same cleaning stations repeatedly, sometimes over a period of years, suggesting they remember the locations and value the service the cleaners provide. The intelligence of manta rays has been documented in various ways. In laboratory settings, mantas have been shown to have excellent learning and memory capabilities. They can be trained to respond to visual cues and remember the training for long periods. In one famous experiment, manta rays were exposed to mirrors and observed engaging in behaviors that suggest self-recognition. They would position themselves in front of the mirror, blow bubbles, and move in ways that seemed designed to observe their own reflection. This kind of behavior is considered evidence of self-awareness and has been documented in very few non-mammalian species. The brain of a manta ray is large relative to its body size, larger than that of most other fish and comparable in relative terms to the brains of mammals and birds. Within the brain, certain structures associated with learning, memory, and sensory integration are particularly well developed. Manta rays also have remarkably acute senses. Their vision is good, and they appear to use visual cues to navigate, identify cleaning stations, and possibly recognize individual members of their own species. Their sense of smell is also well developed, and mantas likely use olfactory cues to locate food and navigate over long distances. Like all rays, mantas possess ampullae of Lorenzini and can detect electric fields, though this sense is probably less important for a filter feeder than for a ray that hunts buried prey. Reproduction in manta rays is slow and infrequent. Females do not reach sexual maturity until they are quite large and several years old, perhaps 8 to 10 years in reef mantas and even older in giant oceanic mantas. Mating behavior can be elaborate. Courtship begins when one or more males pursue a female, sometimes for days. The males follow closely behind the female, matching her swimming speed and direction. Eventually, one male will approach close enough to grasp the female's pectoral fin with his teeth. Using this grip, he maneuvers himself beneath her so that their ventral surfaces are in contact, then inserts one of his claspers to transfer sperm. After mating, the female retains the fertilized egg inside her body. The embryo develops over a gestation period of about 12 to 13 months, nourished first by a yolk sac and later by uterine secretions. When the pup is born, it emerges folded, with its pectoral fins wrapped around its body to ease passage through the birth canal. But within moments of birth, the pup unfurls and begins to swim. It is fully formed, a miniature version of its parents, capable of feeding and swimming on its own. The mother provides no parental care after birth. The pup is immediately independent, though it faces many dangers in its first months of life. Females typically give birth to just one pup at a time, occasionally two, and they do not reproduce every year. Some females may have intervals of 2 or more years between births. This slow reproductive rate makes manta populations vulnerable to overfishing and other human impacts. Despite their size and apparent power, manta rays are completely harmless to humans. Unlike their stingray relatives, mantas have no venomous barb. Their tails are thin, whip-like, and entirely non-threatening. Their mouths, though large, are filled with tiny non-functional teeth that play no role in feeding. A manta ray is a gentle giant, subsisting entirely on some of the ocean's smallest creatures and posing no danger to anything larger than a millimeter or 2 in size. Divers who encounter manta rays often describe the experience as one of the most moving of their lives. To see a creature so large moving with such grace, to watch it glide effortlessly through the water with slow, powerful beats of its enormous wings, is to witness one of the ocean's most elegant spectacles. While manta rays have taken to the open ocean, most rays remain faithful to the lifestyle of their ancestors, life on or near the seafloor. The stingrays represent this bottom-dwelling tradition in its most familiar form. There are many families and hundreds of species of stingrays, found in nearly every marine environment from shallow tide pools to depths of hundreds of meters. Some have even adapted to freshwater, living in rivers and lakes far from the sea. What unites all these stingrays is a basic body plan optimized for life on the bottom. A flattened disc, a long tail, and in most cases, one or more venomous barbs for defense. A typical stingray has a rounded or diamond-shaped disc that is widest near the middle and tapers toward the tail. The pectoral fins extend around the sides of the disc, while the smaller pelvic fins are located near the tail. The tail itself is one of the stingray's most distinctive features. It's long, thin, and flexible, often as long as or longer than the disc itself. Along the dorsal surface of the tail, usually close to the base, are one or more barbs. These barbs are modified scales, each one composed of a hard, bony core covered by a thin sheath of skin and tissue. The barbs are serrated along both edges with sharp, backward-pointing teeth that make them difficult to remove once embedded. The skin sheath covering the barb contains cells that produce venom, a complex mixture of proteins and other compounds designed to cause pain and tissue damage. When a stingray is resting peacefully, its tail lies flat on the bottom or curves gently away from the body. But if the ray is threatened, stepped on, or grabbed, it reacts with startling speed. The tail whips upward and forward, arcing over the body and driving the barb into whatever is threatening the ray. The force behind this strike can be considerable, enough to penetrate thick rubber, wood, or even bone. Once the barb enters tissue, the serrations anchor it in place, and any attempt to pull it out causes further tearing and damage. At the same time, the skin sheath ruptures, allowing venom to flow into the wound. Stingray venom is painful, intensely so. People who have been stung describe the sensation as burning, throbbing, or shooting pain that radiates from the wound and can last for hours or even days. The venom causes local tissue damage, swelling, and sometimes necrosis, the death of cells around the wound site. In severe cases, especially if the sting occurs in a sensitive area like the chest or abdomen, the venom can affect the heart and breathing. However, deaths from stingray stings are rare. Most stings occur on the feet or ankles when someone accidentally steps on a buried ray, and while extremely painful, these wounds are not usually life-threatening. It's important to understand that stingrays are not aggressive. They do not seek out conflict with humans or other large animals. The barb is purely defensive, a last resort used only when the ray feels threatened and has no other option. Stingrays prefer to avoid confrontation. When they sense vibrations in the sand that might indicate an approaching predator or person, they often swim away. But if escape is not possible, if they are pinned down or stepped on, they defend themselves with their tail. From the ray's perspective, this is entirely reasonable. A stingray has few other defenses. It cannot bite. It has no claws or spines. The venomous barb is its only weapon. The barb itself is a remarkable structure. It is not permanent. Stingrays shed and replace their barbs periodically, often once or twice a year. A new barb begins to grow beneath the old one, and when it reaches sufficient size, the old barb is sloughed off. If a ray loses its barb in defense, breaking it off when it strikes a predator or a person, a replacement will grow in over a period of several months. This ability to regenerate the barb ensures that a stingray is never permanently defenseless. Most stingrays spend the majority of their time resting on the bottom, often partially buried in sand or mud. Burying serves multiple purposes. It conceals the ray from both prey and predators, making the ray nearly invisible as it lies motionless on the seafloor. It also protects the ray from strong currents and reduces the energy required to maintain position. To bury itself, a ray settles onto the bottom and then uses gentle undulations of its pectoral fins to flick sand over its body. Within moments, only the eyes, spiracles, and sometimes the tip of the tail remain visible. In this buried state, a stingray can wait patiently for prey to come near. The diet of most stingrays consists of bottom-dwelling invertebrates and small fish. Crustaceans are particularly important prey items: crabs, shrimp, prawns, and mantis shrimp. Many stingrays also consume mollusks, including clams, oysters, and snails. To find this hidden prey, a stingray uses its electroreceptive sense. As it glides slowly over the bottom, its ampullae of Lorenzini detect the faint electric fields produced by the muscle contractions and nerve activity of buried animals. When prey is detected, the ray positions itself above the spot and uses a combination of its pectoral fins and its mouth to extract the animal from the sediment. Some species use the tenting behavior described earlier, creating a suction force that pulls prey out of the sand. Others excavate more actively, using their pectoral fins to dig and their mouth to sift through the disturbed sediment. Once captured, hard-shelled prey must be dealt with. Stingrays that specialize in eating mollusks and crustaceans have powerful jaws and flattened teeth that function as crushing plates. The teeth are arranged in a pavement-like pattern, with each tooth fitting tightly against its neighbors. When the ray bites down, the teeth press together, creating a solid surface that can crush even thick shells. After crushing the shell, the ray uses its tongue and the muscular walls of its mouth to separate edible tissue from shell fragments, spitting out the shells and swallowing the soft parts. Reproduction in stingrays involves internal fertilization. As in all rays, males use their claspers to transfer sperm to females, and the females retain the fertilized eggs inside their bodies. Depending on the species, the embryos may be nourished by a yolk sac, by secretions from the mother's uterus, or by a combination of both. In some species, females give birth twice a year, while in others, reproduction is annual or even less frequent. Litter sizes vary widely, from just 1 or 2 pups in some species to a dozen or more in others. The pups are born live, fully formed, and capable of swimming and feeding immediately. They receive no parental care and must fend for themselves from the moment of birth. This might seem harsh, but stingray pups are well equipped to survive. They are born with functional barbs, though these are often covered by a protective sheath that dissolves shortly after birth. They have all the sensory systems and hunting skills they need to find food, and they instinctively bury themselves in sand to hide from predators. Stingrays face many natural predators. Sharks are perhaps their most important enemy. Many shark species, particularly those that feed on the bottom, regularly consume stingrays. Hammerhead sharks are especially fond of stingrays, and their wide, flat heads may have evolved in part to help them pin rays to the bottom. Tiger sharks, bull sharks, and various other large sharks also prey on rays. Interestingly, the barbs seem to offer little protection against sharks. Researchers have found stingray barbs embedded in the jaws, heads, and mouths of sharks, evidence that the sharks either don't care about the sting or can tolerate the pain well enough to continue feeding. Some stingrays have adapted to fresh water, and these river rays represent one of the most remarkable evolutionary transitions in the ray family. The river stingrays of South America, for example, belong to their own family and are found throughout the Amazon and Orinoco river systems. These rays have never been found in salt water, suggesting they have been isolated in freshwater for a very long time, perhaps millions of years. Freshwater stingrays face challenges that marine rays do not. The water is less salty, which affects osmoregulation, the process by which an animal maintains the proper balance of salts and water in its body. Freshwater rays have evolved specialized kidneys and other adaptations to deal with this challenge. Despite the fearsome reputation of their barbs, stingrays are fascinating, beautiful animals that play important roles in their ecosystems. They help control populations of invertebrates, turning over sediment as they feed and creating small disturbances that benefit other organisms. They are, in turn, food for larger predators, linking the energy stored in bottom-dwelling invertebrates to the higher levels of the food chain. And they have endured for millions of years, adapting to countless different habitats, from tropical reefs to temperate estuaries to freshwater rivers. The stingray, lying quietly beneath a layer of sand, is a patient hunter, a successful survivor, and a reminder that even animals equipped with formidable defenses are usually gentle and less provoked. If stingrays represent the archetypal bottom-dwelling ray, then eagle rays represent the transition toward a more active, open-water lifestyle. Eagle rays retain some of the features of bottom-dwelling rays, including the ability to feed on benthic prey, but they spend much of their time swimming actively through the water column, using powerful wing beats to propel themselves with impressive speed. The most familiar and widely recognized eagle ray is the spotted eagle ray, a creature of such striking beauty and graceful movement that it has become an icon of tropical ocean life. The spotted eagle ray has a distinctive appearance. Its body is flattened but thicker through the middle than that of a typical stingray, giving it a more three-dimensional shape. The pectoral fins are long and pointed, extending outward and backward from the head in a shape that truly resembles wings. When an eagle ray swims, it flaps these wings in powerful synchronized beats, rather like a bird in flight. The motion is smooth and efficient, allowing the ray to cover long distances or accelerate quickly when needed. The head is somewhat raised and projects forward from the body, with a blunt, rounded snout that looks rather like a duck's bill. This snout is an adaptation for digging, and eagle rays use it to root through sand and mud in search of buried prey. The dorsal surface of a spotted eagle ray is dark, usually black, deep blue or greenish black, covered with a distinctive pattern of white spots or rings. This pattern is unique to each individual, and researchers use photographs of the spots to identify and track individual rays over time. The ventral surface is white or pale gray, providing the typical countershading seen in many marine animals. The tail is long, thin, and whip-like, extending far behind the body. Near the base of the tail, most eagle rays have one or more venomous barbs, though these are used only for defense and are rarely employed against humans since eagle rays are not bottom dwellers that people might step on. Spotted eagle rays are found in warm, tropical, and subtropical waters around the world, from the Caribbean and Gulf of Mexico to the coasts of Africa, the Indo-Pacific, and the Eastern Pacific. They are often seen swimming over coral reefs, through lagoons, and in shallow bays, though they also venture into open ocean and have been recorded at depths of over 60 meters. Unlike stingrays, which tend to be solitary, eagle rays are often social. They may swim alone, but they also commonly travel in small groups or large schools. When schooling, they swim in formation, each ray positioned slightly above or below and to the side of its neighbor, creating a flowing, coordinated movement that is mesmerizing to watch. The diet of eagle rays consists primarily of hard-shelled mollusks and crustaceans. They use their duck-like snout to dig into the substrate, rooting through sand and mud to uncover buried clams, oysters, crabs, and other invertebrates. Once prey is located, the eagle ray uses a combination of water jets and suction to extract it from the sediment. The powerful jaws and flattened teeth then crush the shell, allowing the ray to consume the soft tissue inside. This diet of shellfish means that eagle rays can sometimes come into conflict with commercial shellfish operations, and in some areas they have been blamed for damaging oyster and clam beds. However, recent studies suggest that the impact of eagle rays on shellfish populations is often overestimated, and that other factors like disease, pollution, and overharvesting are more significant threats to shellfish. Eagle rays are ovoviviparous, meaning that the eggs hatch inside the mother's body and she gives birth to live young. The embryos are initially nourished by a yolk sac, but as the yolk is depleted, they receive additional nourishment from uterine secretions. Gestation lasts about 12 months, after which the female gives birth to between 1 and 4 pups. The pups are born fully formed, with wingspans of about 1 foot, and they are immediately capable of swimming and feeding on their own. Like their parents, they have distinctive spotted patterns from birth, though the spots may change slightly in number and arrangement as the ray matures. One of the most spectacular behaviors of eagle rays is breaching, or jumping completely out of the water. An eagle ray will swim rapidly toward the surface, building speed, and then launch itself into the air, sometimes reaching heights of several feet. It then crashes back into the water with a loud smack that can be heard from a considerable distance. The purpose of this behavior is not entirely understood. It may serve to dislodge parasites, to communicate with other rays, to attract mates, or simply to express exuberance. Sometimes multiple rays will breach in succession, creating a series of splashes that look like synchronized diving in reverse. Eagle rays are generally considered harmless to humans, though caution is warranted. The barbs on their tails are venomous and can inflict painful stings if the ray is threatened or mishandled. However, because eagle rays spend most of their time swimming rather than resting on the bottom, the risk of accidentally stepping on one is low. In areas where eagle rays are common, divers often encounter them swimming gracefully through the water, their spotted wings beating slowly as they glide past. These encounters are usually peaceful and awe-inspiring, a chance to observe one of the ocean's most elegant swimmers at close range. The conservation status of eagle rays varies by species and location. The spotted eagle ray is currently listed as near threatened, meaning it is at risk of becoming endangered in the near future. The primary threats are overfishing, both targeted and as bycatch in fisheries aimed at other species, and habitat destruction, particularly the loss of coral reefs and seagrass beds where eagle rays feed. Like many rays, eagle rays reproduce slowly, with females producing only a few pups every 1 or 2 years. This low reproductive rate makes populations vulnerable to overharvesting, as they cannot quickly recover from declines. In some areas, efforts are being made to protect eagle rays. Certain countries have banned their capture entirely, while others have implemented size limits or seasonal closures. Marine protected areas, where fishing is restricted or prohibited, can provide safe havens where eagle rays can feed, mate and rear their young without disturbance. Ecotourism has also emerged as a powerful conservation tool. In places where divers and snorkelers come to see eagle rays, the economic value of a living ray far exceeds its value as food or as a commodity. This has led to increased protection and a greater awareness of the importance of preserving these magnificent animals. The eagle ray, with its spotted wings and graceful flight through water, represents a kind of bridge between the bottom-dwelling stingrays and the fully pelagic manta rays. It retains the ability to feed on the seafloor, but has also embraced the freedom of the open water. It is equally at home gliding over a reef or soaring through the blue, a testament to the adaptability and evolutionary success of the ray body plan. Among the rays that have partially abandoned the bottom for a more active lifestyle, the cownose rays hold a special place. These rays are named for the distinctive shape of their heads, which feature a pair of lobes that extend forward from the snout and resemble the nostrils of a cow. This unusual head shape gives the cownose ray a unique appearance, one that is instantly recognizable to anyone familiar with these animals. But beyond their odd looks, cownose rays are remarkable for their social behavior, their long-distance migrations, and their importance in coastal ecosystems. The cownose ray has a broad kite-shaped body, with long pointed pectoral fins that taper to narrow tips. The body is somewhat thicker and more three-dimensional than that of a typical stingray, though still clearly flattened. The coloration is generally brown to olive green on the dorsal surface and white or yellowish on the ventral surface. The tail is long and whip-like, with one or more mildly venomous barbs near the base. These barbs are smaller and less formidable than those of many stingrays, reflecting the cownose ray's more active lifestyle, which makes defensive stinging less likely to occur. The most distinctive feature of the cownose ray is its head. The front edge of the head is indented in the middle, creating two lobes that extend forward on either side. These lobes are not just decorative, they play a functional role in feeding. Cownose rays are bottom feeders that specialize in hard-shelled prey, particularly bivalves like clams and oysters, as well as crustaceans. The lobes help manipulate food toward the mouth, which is equipped with powerful jaws and flattened teeth designed for crushing shells. The teeth are arranged in plates, with 7 rows typically present in the cownose ray, each row forming a continuous pavement-like surface. When the ray bites down on a clam or oyster, the teeth press together with enough force to crack the shell, allowing the ray to extract and consume the soft tissue inside. To find their buried prey, cownose rays use a combination of their sense of smell and electroreception. They swim slowly over shallow flats and sandy bottoms, using their cephalic lobes and pectoral fins to disturb the sediment. This creates clouds of sand that temporarily obscure the ray, but also reveal hidden prey. When a clam or other bivalve is found, the ray uses suction to extract it from the substrate, a behavior that can leave distinctive craters in the sand. In areas where cownose rays are abundant, the seafloor can be pocked with these feeding pits, evidence of the ray's constant foraging. Cownose rays are highly social and migratory. They often travel in large schools that can number in the hundreds or even thousands of individuals. These schools are segregated by size and sex, with mature males, mature females, and juveniles often forming separate groups. The rays migrate seasonally, moving northward along the coast in late spring and southward in late fall. This migration is driven by changes in water temperature and likely by the availability of food. During the summer months, cownose rays are abundant in places like the Chesapeake Bay, where they gather to mate and feed in the warm, shallow waters. As autumn approaches and water temperatures drop, the rays move southward to warmer regions where they spend the winter. The migration of cownose rays is a spectacular natural event. Schools of rays swim just below the surface, their wingtips breaking the water as they flap. From above, a large school can look like a flowing river of dark shapes, undulating and shifting as the rays move in coordinated formation. From below, divers describe the sight as both beautiful and slightly eerie, like watching a vast living cloud pass overhead. Mating in cownose rays occurs during the summer, often in estuaries and bays. Courtship can be prolonged, sometimes lasting for days. Multiple males will pursue a single female, following closely behind her and occasionally jostling with one another. The female leads this courtship train, swimming steadily as the males compete for her attention. Eventually, one male will approach close enough to grasp the female's pectoral fin with his teeth. Using this grip, he maneuvers himself beneath her, aligns his body with hers, and inserts a clasper to transfer sperm. After mating, the males typically leave the bay or estuary earlier than the females, heading to other feeding areas. The reasons for this are not entirely clear, but one hypothesis is that the males depart to reduce competition for food, allowing the pregnant females and their young to have access to more abundant resources. The females remain in the bay through the summer, and the following summer, they return to give birth. Gestation lasts about 11 to 12 months, and females typically give birth to a single pup, though twins are occasionally reported. The pup is born fully formed and capable of swimming immediately. It is relatively large at birth, about 1/3 the wingspan of its mother. Cownose rays have some of the slowest population growth rates of any fish. Females do not reach sexual maturity until they are about 7 to 8 years old, and males mature around 6 to 7 years. Combined with the fact that females typically produce only one pup per year, this means that cownose ray populations recover very slowly from declines. This makes them particularly vulnerable to overfishing and other human impacts. In some areas, cownose rays have been blamed for damaging commercial oyster and clam beds, and this has led to culling programs aimed at reducing ray populations. However, scientific studies have shown that the impact of cownose rays on shellfish populations is often overstated. While cownose rays do eat oysters and clams, they typically prefer softshell clams and other bivalves that are less commercially valuable. Hardshell oysters, which are the primary target of commercial fisheries, make up a smaller portion of the cownose ray's diet. Furthermore, oyster populations have declined primarily due to disease, pollution, habitat loss, and overharvesting, not predation by rays. In recognition of the vulnerability of cownose rays and the lack of evidence that they harm oyster populations, some regions have taken steps to protect them. The state of Maryland, for example, has banned cownose ray killing contests, and there is growing awareness that these rays are valuable in their own right, both ecologically and economically. Ecotourism focused on cownose ray migrations has become popular in some areas, with boat tours and dive operators taking people out to witness the spectacular sight of thousands of rays swimming in formation. The cownose ray, with its distinctive head, social behavior, and impressive migrations, is a reminder that rays are not all solitary, sedentary bottom dwellers. These animals are complex, mobile, and deeply integrated into the ecosystems they inhabit. They are also vulnerable, slow to reproduce, and in need of thoughtful conservation if they are to continue their ancient journeys along our coasts for generations to come. For many years, fish were viewed as simple, instinct-driven creatures with limited cognitive abilities. Rays, in particular, were thought to be little more than swimming stomachs, capable of finding food and avoiding danger, but not much else. Modern research has shattered this misconception. Rays, it turns out, are intelligent animals with complex behaviors, sophisticated learning abilities, and in some species, signs of self-awareness that rival those of mammals and birds. The brain of a ray is large relative to its body size, larger than that of most other fish, and comparable in some respects to the brains of mammals. Within the ray brain, certain structures are particularly well developed. The cerebellum, which is involved in coordinating movement, is large, reflecting the complex motor control required to swim with large, flexible pectoral fins. The forebrain, which in mammals is associated with higher cognitive functions like learning, memory, and decision-making, is also well developed in rays. And unlike most fish, rays possess structures called retia mirabilia, networks of blood vessels that may help keep the brain warm, possibly enhancing neural function. One of the most compelling demonstrations of ray intelligence comes from studies of manta rays. In experiments conducted at aquariums, manta rays have been shown to possess excellent learning and memory. They can be trained to respond to visual cues, to approach specific targets, and to perform behaviors on command. More remarkably, they retain this training over long periods. A manta taught to respond to a particular signal will remember that association months or even years later, even without reinforcement. Perhaps most striking is the evidence for self-awareness in manta rays. In a modified mirror test, manta rays were exposed to mirrors and observed to see how they would react. Most animals, when confronted with a mirror, treat the reflection as another animal. either ignoring it or reacting aggressively or fearfully. But a few species, including great apes, elephants, dolphins, and some birds, recognize the reflection as themselves. They engage in self-directed behaviors, positioning themselves to examine parts of their body they cannot normally see, or performing unusual movements while watching the reflection. Manta rays displayed this kind of behavior. When exposed to mirrors, they would swim back and forth in front of the reflection, blow bubbles while watching, and position themselves at angles that suggested they were examining their own bodies. This is considered strong evidence of self-awareness, the recognition that the reflection in the mirror is oneself and not another individual. Self-awareness is a rare cognitive trait, found in very few species, and its presence in manta rays suggests a level of consciousness and intelligence that is remarkable. Beyond laboratory studies, observations of wild rays reveal complex behaviors that speak to their cognitive abilities. Manta rays, as mentioned earlier, return repeatedly to specific cleaning stations, sometimes over a period of years. This requires not only memory but also the ability to navigate across large areas of ocean, to remember the location of the cleaning station, and to understand the value of the service the cleaner fish provide. Some researchers believe that mantas may use a combination of visual landmarks, olfactory cues, and possibly even the Earth's magnetic field to navigate, much as migratory birds do. Rays also demonstrate problem-solving abilities. In aquarium settings, rays have been observed using tools, a behavior once thought to be restricted to primates and a few bird species. For example, a ray presented with a clam that is too hard to crush might carry it to a rock and use the rock as an anvil, repeatedly striking the clam against the hard surface until the shell breaks. This requires not only the recognition that the rock can be used as a tool, but also the motor control to manipulate the clam and the persistence to continue the behavior until the desired result is achieved. Social behavior in rays varies widely among species. Some rays, like many stingrays, are solitary and interact with other individuals only during mating. Others, like eagle rays and cownose rays, are highly social, forming groups that may number in the hundreds or thousands. Within these groups, there is evidence of communication and coordination. Rays appear to use visual signals, such as changes in swimming speed or direction, to coordinate movements. They may also use chemical signals, releasing pheromones into the water that convey information about reproductive status or individual identity. There is even some evidence that rays can produce sounds. While rays lack the vocal apparatus found in many fish, some species have been observed making clicking or popping noises, possibly by grinding their teeth or by some other mechanism. These sounds are within the hearing range of rays, suggesting they may serve a communicative function, perhaps to startle predators or to signal other rays. The emotional lives of rays are harder to assess, but there are hints that these animals experience something we might recognize as emotions. Rays in captivity have been observed to display what appears to be curiosity, approaching divers and investigating new objects placed in their environment. They also seem to form preferences for certain individuals, both human and ray, approaching some more readily than others. Whether this represents true affection or simply learned associations with food or other rewards is difficult to say, but it suggests a capacity for individual recognition and differential response based on past experience. Play behavior has also been observed in rays. Young rays in aquariums have been seen engaging in activities that seem to have no obvious function other than enjoyment. They chase each other, blow bubbles, and manipulate objects in ways that don't lead to food or any other tangible reward. Play is considered a marker of intelligence and well-being in mammals, and its presence in rays suggests that these animals have rich mental lives. The more we learn about ray intelligence and behavior, the clearer it becomes that these are complex sentient beings. They are not mindless automatons, driven purely by instinct. They learn, remember, solve problems, and possibly even experience emotions. This has important implications for how we treat rays, both in captivity and in the wild. It suggests that rays are capable of suffering, that they have interests and preferences, and that their welfare should be a consideration in any activity that affects them. The diversity of feeding strategies among rays is remarkable, reflecting the wide range of habitats and prey they have evolved to exploit. From the filter-feeding manta rays that strain plankton from vast volumes of water, to the stingrays that excavate buried mollusks from the sand, to the eagle rays that crush hard-shelled prey with powerful jaws. rays have mastered nearly every feeding strategy available to a marine predator. At one end of the spectrum are the filter feeders, represented most famously by the manta rays. These enormous rays feed on some of the ocean's smallest creatures, zooplankton. This includes tiny crustaceans like copepods, krill and mysid shrimp, as well as the larval forms of fish, crabs, and other animals. To capture these minuscule prey, a manta must process enormous volumes of water, swimming with its mouth open and funneling water over specialized gill rakers that filter out the plankton. The feeding behavior of manta rays is wonderfully adapted to the patchy distribution of plankton in the ocean. Plankton is not evenly spread through the water. Instead, it tends to concentrate in certain areas and at certain times, driven by currents, upwelling, tides, and the behavior of the plankton itself. Many zooplankton species migrate vertically in the water column each day, rising toward the surface at night to feed on phytoplankton and descending to deeper waters during the day to avoid predators. Manta rays appear to track these concentrations, moving to areas where plankton is abundant and employing different feeding strategies depending on the situation. When plankton is spread diffusely through the water, a manta will often swim in a straight line, mouth open, simply cruising through the water and filtering as it goes. But when plankton is concentrated in a dense patch, mantas employ more sophisticated techniques. One of the most spectacular is somersault feeding, in which a manta performs repeated backward loops, somersaulting through the same patch of water again and again. This behavior serves to stir up the water and concentrate the plankton even further, making each pass through the patch more productive. Sometimes multiple mantas will feed in the same area, each somersaulting independently, creating a chaotic but effective feeding frenzy. Another strategy is chain feeding, in which multiple mantas swim in a circle or spiral, each following the one ahead. This creates a cyclone effect, with water and plankton being drawn into the center of the formation. The mantas swim through this concentrated core repeatedly, mouths open, maximizing their intake with minimal effort. Chain feeding appears to be a cooperative behavior, though it's not clear whether the mantas are actively coordinating with one another or simply responding to the same environmental cues. Manta rays also feed at the surface, a behavior called surface feeding. When plankton is abundant near the water's surface, a manta will swim just below the surface with its mouth tilted upward, skimming the top layer of water. The cephalic fins are unfurled and extended upward, creating a wide scoop that channels surface water into the mouth. This allows the manta to feed efficiently on plankton that might otherwise be difficult to access. At the other end of the feeding spectrum are the benthic predators, rays that hunt prey living on or beneath the seafloor. Most stingrays fall into this category, as do eagle rays and cownose rays. These rays feed on a variety of bottom-dwelling invertebrates, mollusks, crustaceans, worms, and echinoderms. To find this hidden prey, they rely on a suite of sensory adaptations, with electroreception playing a central role. As a ray glides over the seafloor, its ampullae of Lorenzini detect the faint electric fields produced by buried prey. Even an animal completely hidden beneath the sand produces an electric signature from the contraction of its muscles, the firing of its nerves, and the ionic gradients across its cell membranes. The ray's electroreceptors are sensitive enough to detect these minute fields, allowing the ray to pinpoint the location of prey it cannot see, hear, or smell. Once prey is located, the ray must extract it from the substrate. Different species use different techniques. Some use suction, creating a negative pressure that pulls the prey out of the sand and into the mouth. This is often accomplished through a behavior called tenting, in which the ray positions itself over the prey, presses the edges of its pectoral fins against the bottom to create a seal, and then lifts its head. This creates a chamber of low pressure beneath the ray, and sand, water, and prey are all sucked upward into this chamber and toward the mouth. Other rays excavate more actively, using their pectoral fins to dig and their snouts to root through the sediment. Cownose rays and eagle rays are particularly adept at this. Their shovel-like snouts are used to plow through sand and mud, creating clouds of sediment that temporarily obscure the ray but reveal hidden prey. Once a clam or crab is uncovered, it is seized and consumed. Hard-shelled prey presents a special challenge. Mollusk shells and crab carapaces can be thick and strong, requiring considerable force to break. Rays that specialize in eating these animals have evolved powerful jaws and specialized teeth. The teeth are typically flattened and arranged in a pavement-like pattern, with multiple rows of teeth pressed together to create a solid crushing surface. Some species have teeth that are fused or interlocking, further strengthening the bite. When the ray bites down on a shell, the force can be immense, enough to crack even thick oyster shells. After crushing the shell, the ray must separate edible tissue from inedible fragments. This is accomplished using the tongue and the walls of the mouth and pharynx, which are muscular and lined with papillae, small projections that help grip and manipulate food. The soft tissue is swallowed, while shell fragments are either spit out or expelled through the gill slits. Some rays are generalists, eating a wide variety of prey depending on what's available. Others are specialists, focusing on particular types of food. The yellow stingray, for example, feeds primarily on polychaete worms and small crustaceans. The bat ray of the Eastern Pacific specializes in mollusks and crustaceans, using its powerful jaws to crush clams, mussels, and crabs. The Atlantic stingray is more of a generalist, consuming worms, mollusks, crustaceans, and small fish. Diet can also vary with age and size. Young rays often feed on smaller, softer prey than adults. As they grow and their jaws become more powerful, they shift to larger, harder-shelled prey that juveniles cannot handle. This ontogenetic shift in diet reduces competition between different age classes and allows rays to exploit a wider range of resources. Interestingly, some rays have been observed feeding on fish, either catching them actively or scavenging on dead or dying individuals. While this is not the primary diet for most rays, it demonstrates their adaptability and opportunism. A ray is capable of taking advantage of whatever food sources are available, switching between prey types as abundance and availability change. The impact of ray feeding on ecosystems can be significant. By consuming bottom-dwelling invertebrates, rays help regulate the populations of these animals, preventing any one species from dominating. The feeding activity of rays also physically disturbs the sediment, turning over the top layers and creating small-scale heterogeneity in the seafloor. This disturbance can benefit other organisms, exposing buried nutrients, creating microhabitats, and facilitating the colonization of sediments by larvae and other settlers. In turn, rays themselves are prey for larger predators. Sharks are the primary predators of most ray species, with some sharks specializing in ray hunting. Hammerhead sharks, for example, are particularly adept at catching rays, using their wide, flattened heads to pin rays to the bottom before biting. The great hammerhead is known to feed extensively on stingrays, and researchers have found stingray barbs embedded in the mouths and heads of these sharks, evidence of the rays' attempts to defend themselves. The reproductive strategies of rays are as varied as their feeding strategies, but all share certain common features. All rays practice internal fertilization, a relatively rare strategy among fish. Males possess a pair of claspers, modified extensions of the pelvic fins that are used to transfer sperm directly into the female's reproductive tract. This requires close physical contact between male and female, and in many species, mating involves the male grasping the female with his teeth and holding her in position while copulation occurs. Courtship in rays can be brief or prolonged, depending on the species. In some species, males and females simply encounter each other, mate, and part ways with little ceremony. In others, courtship is elaborate and may involve displays, chasing, and competition between males. The manta ray courtship trains described earlier, in which multiple males pursue a single female for days, represent one extreme. At the other end are species in which males simply approach receptive females opportunistically, with little in the way of ritual. The use of teeth during mating is common among rays and can result in visible bite marks on females. In some species, these mating scars are used by researchers as an indicator of sexual maturity. A female that shows bite marks on her pectoral fins is assumed to have mated and therefore to be sexually mature. The teeth of male rays are often more pointed or more robust than those of females, an adaptation for gripping during mating. After mating, the fate of the fertilized eggs varies depending on the species. Rays are divided into two broad reproductive categories: oviparous species, which lay eggs, and viviparous species, which give birth to live young. Oviparous rays, which include skates and a few other groups, produce eggs enclosed in tough, leathery cases. These egg cases are often rectangular with tendrils or horns at the corners that help anchor them to rocks or vegetation. The cases are deposited on the seafloor, and the embryos develop inside over a period of weeks or months, nourished by a yolk sac. When development is complete, a miniature ray hatches from the case and begins its independent life. Viviparous rays, which include most stingrays, eagle rays, and manta rays, retain the eggs inside the female's body. The embryos develop in the uterus, and the female gives birth to live young. The nourishment provided to the embryos varies. In some species, the embryos rely entirely on a yolk sac, and once the yolk is exhausted, they simply wait until they are large enough to be born. This is called ovoviviparity, or a placental viviparity. In other species, the embryos receive additional nourishment from the mother. This can take the form of uterine milk, secretions from the walls of the uterus that the embryos absorb. In a few species, a placenta-like structure forms, connecting the embryo to the mother and allowing for direct transfer of nutrients. This is called placental viviparity and is quite rare among fish. Gestation periods in viviparous rays are long, often lasting many months or even more than a year. Manta rays, for example, have a gestation period of about 12 to 13 months. During this time, the female must carry the developing embryo while continuing to feed, migrate, and avoid predators. The energy investment required is considerable, and this is one reason why rays reproduce slowly. Litter sizes vary widely. Some species produce just 1 or 2 pups per litter, while others may produce a dozen or more. In general, larger species tend to have smaller litters, while smaller species have larger litters. The pups are born fully formed, with all the anatomical features and behaviors they need to survive. They are miniature versions of adults, capable of swimming, feeding, and defending themselves from the moment of birth. There is no parental care in rays. Once the pups are born, they are on their own, and the mother provides no further assistance. The independence of ray pups is both an advantage and a challenge. On the one hand, it frees the mother to resume feeding and preparing for the next reproductive cycle. On the other hand, it means the pups face a perilous early life with no protection. Predation on young rays is high, and many do not survive their first year. Those that do must grow quickly, feeding intensively to reach a size at which they are less vulnerable to predators. Sexual maturity in rays is reached relatively late compared to many other fish. Stingrays may mature at 3 to 5 years of age, eagle rays at 5 to 8 years, and manta rays even later, perhaps not until they are 8 to 10 years old or more. This late maturity, combined with long gestation periods and small litter sizes, means that ray populations grow slowly. A female ray may produce only a few offspring per year, and if mortality is high, the population may not replace itself. This slow reproductive rate has important conservation implications. Rays cannot quickly recover from population declines caused by overfishing or habitat loss. If too many rays are removed from a population, it may take decades for the population to recover, even if all fishing stops. This makes rays particularly vulnerable to overexploitation and highlights the need for careful management and conservation. Some rays have seasonal reproductive cycles, mating and giving birth at specific times of year. This is particularly common in species that live in temperate waters where environmental conditions vary with the seasons. In tropical species, reproduction may be more continuous, with females able to mate and give birth at any time of year. The timing of reproduction is often linked to environmental cues such as water temperature, day length, or food availability. By timing reproduction to coincide with favorable conditions, females increase the chances that their pups will survive. The lifespan of rays varies by species, but many can live for a considerable time. Smaller species may live 10 to 15 years, while larger species like manta rays may live 25 years or more, possibly even longer in the absence of fishing pressure. The slow growth, late maturity, and long lifespan of rays are characteristic of what biologists call a case-selected life history strategy. This strategy involves producing few offspring but investing heavily in each one, with the expectation that those offspring will have a high probability of surviving to adulthood. It is a strategy that works well in stable environments but can be disastrous when faced with rapid changes like intensive fishing. The world's rays face a multitude of threats, many of them linked to human activity. Overfishing is perhaps the most direct and immediate threat. Rays are caught in fisheries around the world, both as targeted species and as bycatch. In some regions, ray meat is considered a delicacy and commands high prices in markets. In others, rays are caught for their cartilage, liver oil, or skin. But perhaps the most valuable and most threatened trade involves the gill rakers of manta rays and their close relatives. In certain parts of Asia, particularly China, manta ray gill rakers are used in traditional medicine. They are believed to have health benefits, though there is no scientific evidence to support these claims. The demand for gill rakers has driven a lucrative and devastating trade. A single manta ray can yield several pounds of gill rakers, which can sell for hundreds of dollars per pound. This creates a powerful economic incentive to catch mantas, and populations in many parts of the world have declined steeply as a result. Both the giant oceanic manta and the reef manta are now listed as vulnerable on the IUCN Red List, meaning they face a high risk of extinction in the wild. Beyond targeted fishing, rays are caught incidentally in fisheries aimed at other species. Bottom trawls, gill nets, long lines, and other fishing gear can catch rays indiscriminately. In many cases, the rays are simply discarded, dead or dying as unwanted bycatch. Even when rays survive being caught, the stress and injury can reduce their chances of survival. Their catch is particularly problematic because it often goes unrecorded and unregulated, making it difficult to assess its full impact on ray populations. Habitat destruction is another major threat. Many rays depend on coastal habitats like estuaries, mangroves, seagrass beds, and coral reefs. These habitats are under intense pressure from human development. Coastal construction, dredging, pollution, and the conversion of wetlands for agriculture or aquaculture all reduce the availability of suitable habitat for rays. Coral reefs, which are important feeding and cleaning areas for many rays, are declining worldwide due to climate change, overfishing, pollution, and disease. Climate change poses additional challenges. Rising ocean temperatures can alter the distribution of prey species, forcing rays to shift their ranges or modify their behavior. Ocean acidification, caused by the absorption of excess carbon dioxide from the atmosphere, can affect the availability of calcium carbonate, which many of the mollusks and crustaceans that rays feed on need to build their shells. Changes in ocean currents and upwelling patterns can alter the distribution of plankton, affecting filter-feeding rays like mantas, and the increasing frequency and intensity of storms and other extreme weather events can disrupt breeding and feeding areas. Pollution is a pervasive threat. Chemical pollutants like heavy metals, pesticides, and industrial chemicals accumulate in marine food webs, and top predators like rays can accumulate high levels of these toxins in their tissues. Plastic pollution is also a concern. Rays have been found with plastic debris in their stomachs, and filter-feeding species like mantas may be particularly vulnerable to ingesting microplastics. The impacts of these pollutants on ray health are not fully understood, but they likely include reduced reproductive success, weakened immune systems, and increased susceptibility to disease. Despite these many threats, there are reasons for hope. Conservation efforts for rays are growing, driven by increased awareness of their ecological importance and their vulnerability. Many countries have implemented protections for rays, banning their capture or placing limits on fishing. International agreements like TITES, the Convention on International Trade in Endangered Species, now regulate the trade in manta rays and other threatened species, making it illegal to trade their parts across international borders without proper permits. Marine protected areas, where fishing and other extractive activities are restricted or prohibited, provide safe havens for rays. In these areas, ray populations can recover, and the rays can carry out their life cycles without the constant pressure of fishing. Studies have shown that marine protected areas can be highly effective at restoring ray populations, particularly when they are large, well enforced, and situated in areas important for ray feeding, breeding, or migration. Ecotourism has emerged as a powerful conservation tool. In many parts of the world, people are willing to pay significant sums to see rays in the wild. Diving with manta rays, for example, has become a major draw for tourists in places like the Maldives, Indonesia, Hawaii, and Mexico. A study in the Maldives found that a single reef manta ray, over the course of its lifetime, could generate more than $1 million in tourism revenue. This is far more than the same ray would be worth if killed for its gill rakers. When local communities see the economic value of living rays, they are more likely to support conservation efforts and to resist the temptation to fish them unsustainably. Education and awareness are also critical. Many people are not aware of the threats facing rays or of the important roles these animals play in marine ecosystems. By raising awareness through documentaries, social media, school programs, and public outreach, conservationists can build support for protective measures. When people understand that rays are intelligent, long-lived, and vulnerable, they are more likely to care about their fate and to take action to protect them. Research is another essential component of conservation. To protect rays effectively, we need to understand their biology, their movements, their habitat needs, and the threats they face. Scientists around the world are working to fill these knowledge gaps, using techniques like satellite tagging to track ray migrations, genetic analysis to understand population structure, and long-term monitoring to assess population trends. This research provides the information needed to design effective conservation strategies and to measure their success. Ultimately, the fate of rays will depend on the choices we make. If we continue to overfish them, destroy their habitats, and pollute the oceans, ray populations will continue to decline, and some species may disappear entirely. But if we choose to protect them, to manage fisheries sustainably, to preserve critical habitats, and to reduce pollution and greenhouse gas emissions, rays can recover and thrive. The graceful creatures that have glided through the world's oceans for hundreds of millions of years can continue to do so, delighting future generations and playing their vital roles in the ecosystems they inhabit. And so we've drifted through the world of rays, from the gentle giants that are manta rays to the quiet stingrays resting beneath the sand, from the soaring elegance of eagle rays to the graceful migrations of Kaunos rays. We've explored their ancient lineage, their remarkable anatomy, their intelligence and complex behaviors, their diverse feeding strategies, their slow and careful reproduction, and the many challenges they face in a rapidly changing world. These are animals of extraordinary grace and beauty, shaped by hundreds of millions of years of evolution into forms perfectly suited to life in the ocean. They are not simple creatures. They are intelligent, aware, capable of learning and memory, possibly even of self-awareness. They are builders of ecosystems, predators and prey, migrants and homebodies, solitary wanderers and social travelers. Tonight, as you drift towards sleep, perhaps you can carry with you an image of a manta ray gliding through clear blue water, its enormous wings beating slowly, its spotted pattern catching the filtered sunlight. Or a stingray, buried in the sand, only its eyes visible, waiting patiently for the faint electric whisper of hidden prey. Or a school of eagle rays, their wings flashing white spots as they swim in formation through a coral canyon. You are a part of this ocean world, connected to these creatures by the chemistry of life, by the water that flows in your blood and theirs, by the shared history of all living things. The rays, like you, are travelers through time, carrying within them the legacy of countless generations, moving forward into an uncertain future. If you happen to still be awake, you can go ahead and watch the next chapter now. Sleep well, and dream of the graceful world beneath the waves. Good night.